Welcome to the Clima podcast. In this episode, I speak to Graham Finch. Graham is the Principal Science Specialist at RDH in Vancouver. He holds a Bachelor of Applied Science, Civil Engineering, and a Master of Applied Science, Building Science Engineering. In this interview, we delve into the complex topic of rain screens. Clima inspires and educates people to create healthy, durable and energy-efficient buildings to live, learn, work and play in. All right, Graham, well, welcome to the Clima podcast.
Thanks for having me, Simon.
Now, Graham, just to give my audience a little bit of an idea about yourself, can you think of something that influenced you when you were growing up that will give us a bit of a better picture about you?
Yeah, so I'm a building scientist and really interested in buildings and in architecture. And as a kid, I think I always wanted to be an architect or a builder. Spent a lot of time in my youth and childhood building things. So I built race cars and carts and a lot of tree forts. So probably influenced me into getting into building science and architecture, and where I am today.
Today, we're going to talk a little bit about facades and specifically rain screens. So I wonder if you can start off by giving us a little bit of a background about some of the issues with face-fixed facades and how this sort of led to the use of rain screens.
I'm in Canada, but also done work in New Zealand as well. And, where we are in the world, there's lots of different ways to build a wall facades. And, a period of time, and even in the past, and even today, a face sealed wall where we've seen a lot of problems. And the face sealed wall is essentially where you got cladding, you're directly fixed to the wall, and you're relying on that cladding to be perfectly watertight forever, to be, keep the water out. But the reality is materials break down, especially seals and, interfaces with windows and flashings and places where over time water can get in, or even initially, water can get in. And once water gets into a face seal assembly, it fails. And we actually had a really neat litigation case in New Zealand a number of years ago. Spent a decade working on it. And the whole issue was face seal walls. Water got in, couldn't get out, made things bad, right? And, if they just spaced off that cladding in these buildings, they would have been fine. And actually, a lot of the research we found through that found that they just put a rain screen on these buildings, they would not have had any of the issues that they saw, and a number of failed buildings from that. So when you get face seal systems, they are problematic because they're relying on a single line of defense, and construction is imperfect, especially with wood frame construction and the way we detail claddings, windows, water gets in. And so we need to let it get out. And the industry has shifted in the last couple of decades to always providing redundancy and backup. First and secondary line of protections, or primary and secondary way of managing water. That's where we've gone, and that's why we have rain screen walls.
So as a definition of a rain screen, what are the sort of components that come together to form the rain screen?
There's lots of definitions. You Google rain screen, you will find lots of different definitions. And there's some good, there's some bad ones. You actually see in North American to Oceania to European differences in definitions, but they are essentially all the same thing. We mean the same thing. But, by fundamental definition, with a rain screen, you've got a outer layer, right? And call it your cladding or your screen, okay? And you got an inner layer, and there's a separation between the outer and inner layer. And the inner layer was typically our backup wall assembly, maybe the house wrap on the sheathing, the studs, concrete block or with membrane on it. So you got a backup, and we got a layer on the front, and it's separated by an airspace, a gap. You create a gap with some sort of means, lots of different ways to do that. And that gap allows drainage and then the passive removal of vapor as well, so ventilation. So we have drainage and ventilation in an airspace between a cladding and a backup, right? So that universally, a rain screen essentially is a screen, it provides two planes of protection of rain against a backup assembly. And you look at the definitions and they're like, people immediately will lumped in pressure equalized rain screen and act ventilated rain screen and all these different, definitions of rain screen. They're all fundamentally the same: drainage, ventilation behind a cladding and protecting essentially over a backup. There's lots of different ways to achieve that. they're all essentially the same. And you guys call things a bit different than we call things up here. So we're all upside down, but call it back ventilated, but it's essentially drainage and ventilation are fundamental to that. And a lot of the work that I've done, research, grad work, demonstrated universally that you need both those things for a rain screen to work.
It's quite interesting you mentioned that, talking about the different terms. So in New Zealand at Clima, we've been calling the building wrap the weather resistive barrier. And I see you guys refer to it as a water resistive barrier. What were you discussing? What are the reasons that you're using the term water rather than weather?
Yeah, I'm sorry. The term weather isn't quite correct. It is supposed to be water. And there's been so much debate on this over the last decades. And not to throw you under the bus, but the reason it's a water resistant barrier is the primary function of the water resistant barrier, the WRB, sometimes called secondary plant protection, is for water control. Say it's secondary for water control. Now, you can also do other things with that. You can control air. And so you can be a party air barrier. It could be vapor permeable or impermeable. It could also be your vapor barrier, so to speak. So you got, air, water, and potentially vapor control. And so what happens is, when people can, put together air, water, vapor control, it's just easier to say weather, right? But the reality, weather, it doesn't just address weather, right? It's really focused in on water. And that's really where the primary focus. Now, it may have secondary things, but so a water resistant barrier is that inner plane. So we talk about a rain screen definition, that house wrap, whatever it is, your product, others, that is your WRB. At least WRB is the same for it, whatever you want to call it. But whether it's water or weather, or, people, we make slights all the time, but it's water control. You may do other things, but it's really they're fundamentally for water control. And you have to have a WRB in a rain screen.
Now, there's open jointed and closed rain screens, aren't there? Can you explain how that works?
Yeah, so with a rain screen, the cladding that you put on the outside, whatever it is, metal, fiber cement, wood, stucco, brick, stone, glass, whatever the cladding is, the joinery impacts how much water gets through, right? So if you look fundamentally, if you have big sheets of material and you lap them, there's not a lot of holes, right? So that's pretty closed off. There are a lot of claddings that we use nowadays in sort of a modern aesthetic where all the little panels, little rectangles, boards, large boards, small boards, pieces of wood, and we'll intentionally leave joints. And then we'll leave the joints and we might put something lap behind it so we don't see through, or we might not, and let's leave it wide open. And in those cladding systems, we call these open rain screen. And the open rain screen is really an aesthetic. And from a rain screen standpoint, your cladding isn't really keeping a lot of water out, right? So an open rain screen, it's all about, with the cladding, how much water gets through. With an open rain screen, a lot of water goes through. The amount of the rain that hits the wall, say 50, 80% goes through, versus like a lap siding, 1% of the water might get through. So when you look at rain screen designs with open rain screen claddings, the difference is you're putting a lot more water into the rain screen, which means your WRB needs to do a lot more. And so you're shifting a lot of load to the WRB, and that WRB needs to be really good. And you also might call that a weather resistant barrier there, because you actually are seeing UV and you're seeing more loads. And so that WRB needs to be UV stable, and it's going to seal out more water. So it needs to be a bit more robust than, maybe just a paper. And that's where we see challenges with open rain screens, is the backup wasn't designed for the amount of water that's coming through. And they can be very great and elegant and look really nice. But if you don't detail the backup water management, it's almost as bad as a face seal. You can mess it up because now you pushed all the water to a membrane, and that membrane, if that breaks down, it's game over.
So having a look at the different loads that we are expected to protect from, can we start by having a look at the structural side of the rain screen? What can you tell us about claddings and the fastenings?
When you look at the loads on a rain screen, right? So you've got, from a structural standpoint, most people think of wind, right? But, first and foremost, you've got gravity, the weight of that cladding. You've got wind. You potentially have seismic loading, the acceleration of that material, either from the backup wall or itself on the rain screen. You've got potentially also got loads from blast loads and other applications where you might have, unique cases. But, primarily looking at, the weight and then the light dead loads there. You just get wet and dry and stuff like that. And then wind. And you also look at thermals. Well, things expand and contract, and that puts forces on the backup and the cladding itself. And see a lot of failures there where things expand and the backup doesn't allow it to expand and cracks and falls off. So you're designing for, wind, so it doesn't get sucked off typically or really damaged by the wind or flexing so too much, and the weight itself. So you're essentially hanging this cladding into the backup, right? So your loads from your cladding have to transfer through from the cladding to your backup. And nowadays we tend to use, cladding attachments for exterior insulation or to create the rain screen space. So the structural load from, say, a screw or a nail in the fastener needs to transfer through to the backup. And all of those connections need to be engineered. Otherwise, things can fall off or get sucked off buildings.
Next up, what about fire? Obviously, we've seen some pretty catastrophic sort of disasters recently. What's important around designing for fire?
Fire, especially in taller, larger buildings. And now the codes across the world are, have different requirements depending on area, but essentially they have similar fundamental requirements. And the fundamental requirements is, depending on the type and height of the building, the cladding may need to be non-combustible, or in some cases, it might need to be ignition resistant, right? So it's a lower combustibility. And there are cases where you can use combustible, things like wood as well. But as we get into taller, larger buildings where these fire codes would, say, apply for your project, the cladding combustibility and the materials that make that up are important. And then the supports, the attachments, but then the gap, right? And so when you look at the rain screen cavity in the gap, generally, if the cavity is less than 25 millimeters, it's hard for fire to propagate within that cavity unless you have a lot of combustible materials in there. So if you use a non-combustible cladding with a smaller gap, 19, 20 millimeters to 25 millimeters over non-combustible insulation or WRE or backup, generally you're pretty safe. And that's sort of like, you look at the assemblies that are, you sort of deem fire resistant, that's what they are. Now, to use, say, foam plastic insulation or certain water resistant barriers, you might need to do some testing. And they'll tell you that, that gap matters, right? A 50 millimeter gap or a 75 millimeter gap creates a chimney and could be quite dangerous in a fire. And so if you look at fires that have happened, scary videos of things of people being there, seeing these fires go to buildings, they were generally combustible claddings, even though they were like metal, but the plastic in the middle of the metal that gave it the strength was combustible at a certain temperature, or the insulation in the backup was combustible, or in a lot of cases, they had big gaps. They had the created chimneys where the fire could then travel up. And so you need fire blocking, at each floor to prevent the fire. If there's a fire from going through New York, they've added specific requirements to actually block off rain screens to some respect, which creates some other challenges. But, generally, you got to watch the cladding, backup materials in there, and the cavity size. And a rain screen can be completely safe in a facade fire. It's about controlling those variables, but you can also make it quite dangerous, and you can also make it more dangerous than, say, a J-seal type wall if you aren't careful with that. So those things all work in interplay. So there's test standards that sort of evaluate that, but if you keep it non-combustible and non-combustible insulation cladding, you're generally pretty safe.
And then with water, Graham, obviously we've got, rain and wind and things. How does it deal with water?
The cladding?
Oh, the cladding and obviously the weather-resistant barrier behind that.
So in terms of managing water for a rain screen, you get the cladding. We talked about earlier, like the more open it is, the more joints is, the more water it's going through, right? So you can sort of think about the cladding as your, it's a primary plane of protection. And the more water that gets through, the more load on your WRP and your backup, okay? And so generally the first rule as a rain screen is reduce the amount of water getting in there, right? And so wrapping claddings, joints that are baffled, keeping the majority of the water up. Now, if you choose an aesthetic that allows a lot of water in, then you're going to have to do a bit more of the backup. So then, once the water gets into the cavity, you need to make sure that it's not, damaging, wood or supports for cladding attachment or corroding fasteners and getting into spaces there. You also got to keep bugs out, pests. And then you got that load the water on the water resistant barrier. And the water resistant barrier, it's all a matter of, the right material selection, not that it's water repellent, but it's also maybe vapor permeable or impermeable, depending on the rest of your wall design. And then that material and all the details, you're lapping and taking the water that gets in and diverting it back up. So you have flashings, at every floor, typically over window heads, other penetrations where water that gets in, gets out. And so the whole design of a rain screen and water control, you got the cladding, do what you can there, but your main sort of focus is on the backup. You spend a lot of time detailing water getting back out. Now, fortunately, when you're detailing for water, it also often addresses air if you're lapping and sealing. So you often will get dual duty from a water resistant barrier to also be airtight, which is part as well for buildings.
Talking about air, where is your air? What is the consideration around the air barrier placement? Is it on the inside? Is it on the outside? Where would that sit?
The air barrier, sort of theoretically and somewhat fundamentally, is it can go anywhere within your wall assembly. There's a preference in commercial construction. Generally, the air barrier is starting to go more towards the outside of our sheathing and our wall systems. Historically in North America, we put air barrier, especially in Canada, put air control on the inside of our framed wall systems. You look at, mass masonry and European type buildings, people were putting it, maybe on the outside of the concrete block or the masonry there, or the block that was. You look at a lot of buildings in New Zealand, framed walls, whether it be wood or steel stud, there may not have been an air barrier, nothing in there. You probably were relying on gypsum board and ceiling of that. So there are different places and different materials that you end up using in there. And air barriers and rain screens can be completely sort of separated apart. But, rain screen walls generally need an air barrier. It's sort of modern design. And what we'll often do is we'll have the air barrier combined with the water control. The water is just a barrier function in that assembly. So the house wrap will be tape sealed, maybe self-adhered to the sheathing, and that's detailed as our air barrier. And the air barrier is there to prevent air leakage through the building. Lots of reasons for doing that: comfort, energy efficiency, condensation, and then the rain screen is part of that. Now, there's a lot when you start looking into air barriers and rain screens. There's some confusion around pressure moderation, pressure equalization, and where the air barrier has to go. So there's also some theoretical work that's being done looking at air barrier placement, outside, inside, and how water gets through. When you look at rain hitting a building and inside of a wall system, if you have a material that's an air barrier and you have water on it, the pressure drop occurs across that material, right? So you got, say, a house wrap, and it's the most airtight thing you have. If you have water on there, it's going to be easy for that water to get sort of sucked across there. So you have to do a really good job of water control with that air barrier at the same time. So we need to do really good house wrap details. If, say, that house wrap was just there and lapped and the air barrier is somewhere else, there'll be less of a pressure drop across that material, that house wrap. And therefore, the risk of water getting sucked across there is lower because pressure drop doesn't occur. And so, it's hard actually in real buildings to design necessarily where the pressure drop occurs when you have multi-layers of materials, like house wrap, you might have sheathing, you have drywall on the inside, you have other materials. They have another vapor barrier in there that might take some of the air load, depending how you seal it up. So it's hard to actually get the pressure drop to occur where you are unless you have just like one material that's kind of doing everything. And if you have to do a really good job. If you're going to, make something air and watertight, don't half-ass it, right? You gotta go all the way.
So when you're talking about detailing those air barriers and water-resistant barriers, as you call them, what about seismic considerations? What are we needing to design for?
Earthquakes, building movement is as much of a consideration as earthquakes as well, just deflection, live load, and long-term creep, right? A concrete building you'll have floors, so you'll get some deflection. So when you're designing your wall systems, you need to accommodate the movement of the structure. And your walls will either be load-bearing or they'll be non-load bearing, right? And so depending on how your wall structure is taking the loads, you may end up with joints, right, where you need to accommodate movement. And a good example is like curtain wall systems, right? Curtain wall systems are light, they're hung, and they're hung off of heavy buildings. In an earthquake, the building moves and the curtain wall sort of hangs in place. And so you need to design joint area to allow the curtain wall to move and not break, but also remain air and watertight. And so when you look at building movement, whether it be just loads or seismic or extreme events, you'll have joints that move. And so in the rain screen, those joints that move need to be air and watertight for the movement and then over time, for the life of that building. Now, in a small earthquake, a lot of those joints should perform just fine because the loads, will be small, a couple millimeters, and it's sort of in line with the movement you'd see from like normal building movement, right? Light loads and thermal. In big earthquakes, so when you get a lot of movement, it might break those, right? And so you could design those to take that, and we design curtain wall systems that'll accommodate, 50, 75 millimeters, even like, a couple hundred millimeters of movement, depending on the type of structure, with really flexible seals, right? Or things that can slide and then move around there. So you can design to be air and watertight after big events like earthquakes, but you need to understand what the movement is and where it occurs and just design for it.
So what are some of the sort of test procedures you're using and standards to understand this better?
In North America, there are, the number of test standards that you can, ASTM, ALA standards that we use, and in Europe, they're similar, in New Zealand as well. But essentially, you build, you can do engineer things and design things, but the testing is you build these, full-scale mock-ups. You can build smaller ones with small windows and things like that. But you essentially apply the movement loads that you expect in the design of the building to the seals and other aspects of that facade. You essentially simulate an earthquake by a lateral drift. You can go to shake tables, but there's not that many people doing facade research on facade table or on shake tables. But generally, the labs, you'll just move things back and forth. You'll do wind loads in and out. You'll do lateral loads side to side and building movement up and down. And so you essentially force the loads into the facade. And then you do air and water testing throughout that as you do the various tests to demonstrate that it is air and watertight all the way through to, a big earthquake or maybe to a serviceable earthquake, so to speak. So, and it's design of flexible things or things like, that allow that movement. And so things don't need to be perfectly rigid. Maybe it's the way of thinking about it is you don't need everything really rigid and stiff. You want to build in flex, like good tapes and sealants, maybe joints that move a lot where they need to be. And that's part of the facade design.
So what would be a typical lifespan expectancy in the US and Canada for a wall system?
A lot of debate of life expectancy. I mean, you look at, you start with masonry. Masonry, if you use the right brick, the right stone, can last 10 or 50, 100, 200, longer years. I mean, it's demonstration of that. And if you put the wrong bricks, you might get like 10 years, right? Freeze thaw or something like that. But if you choose the right materials like that, and with maintenance, you can make these last a long time. Where we get most of these questions, okay, with like claddings like, fiber cement, metal, high pressure laminates, and all sorts of different, panel type claddings that are thinner and lighter, they all fail slightly differently. And so, whether it be UV, moisture, whatever breaks down the chemistry of that material and metal, and it's not so much breaking down the metal, it's more corrosion or paint failures are usually the problem there. And so with claddings, it's, things become more brittle potentially over time or they corrode. And so what dictates the lifespan of a lot of those buildings is the life of that cladding. So once the cladding looks really bad or falls off, or it's wood cladding, you've had to paint it, 5 times, you're just sick of it, then that's when you end up typically replacing the cladding. Now, the rest of the wall, if we've, say, got a rain screen and good design and water control, is probably okay. Now, time we retrofit, though, we probably want to add some insulation, improve the air tightness, and so there's opportunity there to upgrade when we do that. But a lot of these products, they can last a long time, but they often don't. Or, you hit that sort of like 30-year, 40-year building, and it just doesn't fit architecturally, maybe ugly, it's tacky. And so then you might choose to overclad it, leave the old stuff in or rip down the old cladding. And if you got, nice lightweight claddings, that's fairly straightforward. If you got heavier things, then you might just put something new over top of it. And that's sort of in line with like windows only last, 25, 30, maybe 40 years. And, a window that's like 40 years old and double pane, probably got failed seals, the gaskets and the sealants are all broken down. You can fix a lot of those things, but you're really just limping it on. And so you look at facades and it's like the windows and the walls, when those hit that 30, 40-year mark, hopefully, that's when you start to replace them or overclock them.
So obviously window junctions are a critical area. What are you recommending around the use of what products around window seals? So, we've a whole lot of things. Often we're using a foam or a wet sealant, or there's possibility of tapes that we're looking at. What are your thoughts around those junctions?
Yeah, so when you look at window seals, right, so you got a rain screen wall and your window installation also needs to have rain screen principles, right? And so typically a window nowadays, there's different ways to do this. There's definite variation where you go in the world, but fundamentally you need air and water tightness on the inside seal of the window. And then you would like some drainage on the outside seal, right? So you can have two seals, but you want to typically drain the outer seal. Now, the outer seal typically sees the weather as well. And that outer seal seeing the weather is going to see UV, temperature extremes, right? And so those tend to break down a lot of materials. And, things like polyurethane and acrylic type sealants, you're lucky to get 10, 15 years and you're replacing the sealants there. Silicone sealants will get a bit longer life because they're not organic and UV just break them down, same as other types of sealants. You get a bit longer. But, if you can get rid of the sealants and like actually have, cladding details and stuff that don't have sealants and just the way you do the window trims, then you can get things that last as long as the cladding. Now on the inside, that air and water seal on the inside is hovering around room temperature, right, year round, but it is seeing some extremes as the sun comes in. So there's movement of the building and movement of the window itself, which can put stresses on those seals, right? And so, we're depending on where you go, and here in Canada, it's interesting, like there's a whole area of the country that only does spray foam. And spray foam really doesn't work that well for air. It definitely doesn't work for water. And so you wonder, why they're doing it. That's a lot of, and you see failures to that. And now spray foam alone tends to not work that well, but it works good enough. And that's why I think a lot of people sort of gone that way. We see spray foam and then people add sealant or tape on the inside because they sort of still want to use spray foam. In our climate where it's wet, we typically only use a sealant joint on the inside. And then we drain that out because we do see a lot of water into our rain screen cavities. In drier areas, they might forego that as well. But that inner seal, whether it be sealant, now we see a lot of tapes also being proposed there as well. A tape can do just as well as sealant. It's just the workmanship. We see both. We see, can you get the trade to install the sealant better or the tape better? And then you got some choices there. And the tape you use or the seal you use both has to be very flexible depending on the movement and able to, get nice and tight on day one. And if it's not nice and tight and then fails, then you will get air leakage and potentially water leakage as well.
So what about insulation? So I can see that in your part of the world, there's quite a big movement towards external insulation. Most of our insulation would be done within the framing. How have you guys gone around, promoting that movement towards external insulation? And what are some of the benefits of external insulation?
With exterior insulation in wall systems, no. Concrete, kind of got to put the insulation somewhere, right? It's not in the concrete generally. That's the sandwich metal. But generally, we always have been putting insulation on the outside. You can put it on the inside too, but in a cold climate, it's better on the outside. With steel framing, insulation within the studs, you get a fraction of the R value, right? You put in like an R20 or an RSI, 3.5, it's 3 units there. And you're getting maybe in a taller building, 20, 30% of the effective R value. There's just so much thermal bridging through the steel and the slab edges and all the window details, perimeters that insulation is really not providing much thermal value because of all the thermal bridges. With wood frame construction, putting insulation in studs isn't terrible. This is a thermal bridge, but it's not terrible. It's a palatable thermal bridge. You're losing 20, 30%, right? So what's happened in North America, in particular Canada, is our energy codes have been changing or requiring higher and higher R values for all construction types. And when you look at the R value requirements for construction types, you can no longer stuff enough insulation into wood studs. You never could have in steel, and you always needed to put it somewhere with concrete or mass timber, something like that. So the whole market in the commercial sector for a decade and a couple decades now has been using exterior insulation to hit those R values. Now, as the code increases, or say you're going for passive house or you're going for net zero, you just put more exterior insulation. The only time that we really count for the insulation in the stud cavity is, it would say, wood framing. And steel studs, we might keep it in there for acoustics, but really the thermal performance is largely on the exterior of wall assemblies in Canada and much of colder parts of North America, and even in the southern parts of the US, where just energy codes have gone to a point, there's an appreciation and understanding of thermal bridging. It's now running on the outside. So once you have exterior insulation, that insulation is in your rain screen cavity, right? So before you might have had cladding 25 millimeters WRB. Now you have, 200 or maybe 100 millimeters of insulation in that wall assembly. Now, you can either put that on the outside of the water resistant barrier or on the inside. And the decision is like, can it get wet, right? Wood fiber insulation inside of WRB, mineral wool foam generally outside of the WRB. Once you think about this, now you've gone from a gap that was small to a gap that's actually quite large. And the great thing about exterior insulated rain screens is you have geometry on your side, keeping the water that wants to come in from the outside away from where you're controlling water as a backup. And so we've done a lot of testing to show that exterior insulation really helps water management as a sort of byproduct of just putting it in that space.
So how quickly, for example, if you've got rock wool in your cavity which is exposed to the water, how quickly is that able to actually shed the water out of the system?
Rock wool is probably one of the exterior insulation that we use the most here in larger buildings and have been for 25, 30 years now. And you get that question a lot. What if the mineral wool gets wet, right? And so when you look at rock wool as a product, there's binders in there and also water repellent, basically oil, different types, that when the water hits it, it tends to beat off and burn down. But, if you get a lot of water in it, you can sort of see the water, getting into it a bit. If the UV breaks it down a bit, water will get in as well. No, water will get in, and then it also, because it's the way the product material, it's vapor permeable, so that actually could dry out. So the water gets into it, and then once you get a temperature gradient or vapor pressure gradient, you essentially push the water out pretty quickly. And so with, say, a closed rain screen or a rain screen with good lapping, the mineral wool might not ever get wet. It's just humidity in there, and that doesn't really impact the performance of that mineral wool. If you had an open rain screen and say you allow a lot of water to get in and maybe UV, then you can get water into that, and then you have to dry it out by essentially solar heating or diffusion to essentially dry it out. So, it dries out, but you do need to make sure the UV is not seeing the insulation there as well. Now, with foam plastic insulation, if visibly more water repellents on the surface, water doesn't go through it, as easily. It's really only vapor that moves water through foam, or it gets through the joints and everything. With foam plastic insulation, it's more about insulation, water getting into the joints, and then behind the insulation. And then how do you dry it out of there? Maybe it's gaps, or you're relying on diffusion. With mineral wool, it's drying mineral wool out in different assemblies. It's more about diffusion. You do get drainage through the insulation itself. The diffusion is really what drives that out. So the sun comes up, or there's a temperature gradient across the insulation, the vapor just gets pushed out. So, tens of thousands of buildings with different types of exterior insulation, in Canada, and it's not really a problem unless you do something really stupid, dump a lot of water, or it's sloped, think like a roof, not a roof, not a roof or not a wall, but a roof, right? So, and the roof, it's more like a roof. And if you dump a lot of water into any type of insulation on a roof, it can't get out. That's where you have the problems. So even a rain screen can't stop stupid, right?
Now, in New Zealand, we've still got a lot of drained cavities rather than ventilated cavities. Can you explain how by venting the cavity at the bottom and the top improves the airflow?
A drain system obviously has drains at the bottom. A vented system or vented rain screen also is just vents at the bottom as well. A ventilated rain screen has vents at the bottom and the top. And so you get actually airflow in there. What the difference between a drained and vented rain screen versus a drained and ventilated rain screen is the amount of airflow that occurs in the cavity, right? What's driving that airflow is actually just thermal and moisture buoyancy, right? It's like stack effect, right? Which essentially is the air heats up in the cavity, the sun or temperature difference, and yet that hot air rises and it goes out the top and pressure comes in at the bottom. So with a ventilated rain screen, you'll see 10, 100 or more air changes per hour. That means that for every hour, that whole volume of air changes maybe 10, 50, 100 times. In a vented rain screen, so you don't have vents at the top, the air tends to be stagnant, okay? And that stagnant air sitting there goes in and out the bottom vents slowly by buoyancy and wind generally, okay? So you get, or even barometric pressure changes, which pumps in and out. So you sort of get like a pumping effect. And the result is you get half, maybe 1 or 2 air changes per hour. So significantly less moisture or air exchange. Now, why that matters is if you have moisture in your rain screen cavity, say from water coming in through brick or open rain screen or in a humid environment, what happens in the ventilated case is the humidity and the dew point of that rain screen is very similar to outdoors, right? So essentially bypasses the cladding. And all the moisture in the cladding doesn't really get into the rest of the wall. The problem with a vented case, if you have, let's say, absorptive cladding, is the moisture in the cladding and the backup adds moisture to that cavity, which means the humidity is actually higher, the dew point is actually higher in your rain screen than it is outdoors. And so you've actually created this moisture source by the cladding and the poor ventilation, then that moisture then can diffuse into the rest of your cement. And so we've seen this too, like, you had a masonry cavity and, let's pack in some insulation there in a retrofit. That's like maybe a drained system, probably not. And then the sun hits that brick in the summer and all that moisture blows in and condenses in the wall. If that's ventilated, that vapor that wants to come in from the solar-driven moisture actually will get taken away, right? If you imagine like 100 air changes per hour, like every minute you're getting, quite a big flow. So you're actually getting a pretty good velocity of air taking that moisture out. Now, I will mention that brands in New Zealand have done some of the best research in that. And they looked at, ventilated, poorly ventilated, direct fixed, and vented only. And you see a huge difference in drying times, but also huge difference in performance in the moisture in the rest of the wall. So it matters, and it matters definitely in New Zealand. It matters in coastal regions. You want it to be ventilated because there is that risk that you're going to add more moisture in there.
So is there any specific ratio between the bottom vents and the top vents?
You can get scientific. You can actually do the calculations. When I was in grad school, over 20 years ago now, we were doing this research project looking at the airflow through the vents and the cavity and the top vents. And what we do know is the more restrictive it is, like say you put bug screen or something that's really tight, or like a mesh that, entangled mesh or something that might create your rain screen, the airflow through is quite slow because you've got pressure drop, right? So you think of this like a duct, right? You stuffed your duct, it's full of stuff, and therefore your flow rate drops because the pressure goes up. And so you can actually design that, but generally equal top and bottom vents and nice open cavity. And if you can't get a nice open cavity, then make it bigger, right? Little blocked cavities aren't all that helpful in wet environments. In dry places, in drier parts of Australia, you could definitely get away with just drained and maybe drained and vented because you don't have that moisture load. But in coastal climates, all of New Zealand, it's beneficial to have that ventilation to take away the extra moisture and just provide that extra evaporation in that cavity.
So you mentioned insects. How do you balance then that airflow versus making sure insects don't get in there?
Insects are nowadays wildfire resilience, actually. And the sort of magic is like 1/8 of an inch. 1/8 of an inch works for wildfire. Most bugs, 1/8 of an inch, 3 millimeters. There are bugs smaller, obviously, than that. But like the wasps, the yellow jackets, and the bigger bugs generally don't go through holes that big. So, if you keep your openings 1/8 of an inch, 3 millimeters or smaller, that's generally the effect of bug screen. Now, if you go too small, like you see window screen meshes and stuff like that, the risk with those, on day one, they're not bad, but junk gets in there, and no one ever cleans those, of course. Just construction debris, insulation, stuff like that. Those things get plugged up. And so, you need something that's open and effective there. And you don't want bugs getting in, pests, mice, all, metal screens are generally typically what we use.
And you mentioned earlier a wall versus a roof. What are the typical considerations and how would you design a roof differently to a wall?
The biggest difference is gravity. That's all you got to think about, right? And it's actually how much water goes through that in the wall case, the cladding, versus in the roof place, typically your roof finish, right? So now the roof, think of a metal roof in New Zealand, right? You've got metal roof, and then you hopefully have some sort of underlayment and insulation below that, right? And so if you look at that metal roof with the insulation and the cavity with the slope, the metal being vertical versus on any sort of slope or not dead flat, but very low, you're going to see more and more water go through that. It's not through the metal, but it's through the joinery, the fasteners, the penetrations, the condensation, just, from sweating at night. And so you end up with more water on your water control layer. And so the water control layer, the WRB in a roof, needs to be quite a bit better than one in a wall. Okay. And, the lower the slope and the more the water that can come through, the better that needs to be. And the industry, like there's varying degrees of waterproofness, right? And so, things like plaza decks and stuff like hot rubberized asphalt and things like that, the most waterproof, things like pond liners, right? And then you've got like roof underlayment under shingles, which is not all that waterproof, it kind of sheds. And then you got a lot of stuff in between, right? And you need to pick that in between for the amount of water that gets in there. And where we've seen the most of the messed ups is you design a wall as a roof and you don't change that water control layer, that's where you run into big problems. And so if you just treat it like a roof, everything's lapped, it's probably a bit thicker, it's more water repellent, it's a little more robust. The joints can, move, you're seeing more, thermal movement as well. Putting that below the insulation helps as well. So lots of different ways to design a sloped roof, but whatever your finish is. But that's, again, think of it like a rain screen. That's your cladding, your roofing, and you've got an airspace for drainage and ventilation. The drainage is going to go down a bit more. And then you've got some sort of water control there that that's the last line of defense. Kick the water back out. Nothing's perfectly waterproof, so you got to design for that.
Exactly. Well, Graham, thank you very much for your time. It's been fantastic catching up. Is there anything last thing you'd like to do just to give our audience sort of a key tip around, the way to be doing our rain screens as the best possible method?
There's a lot of focus right now in our market on carbon, especially embodied carbon. And what that means is it puts more focus on to natural bio-based materials as, say, a cladding or an insulation in there. When you look at carbon and durability and carbon efficiency, durability is key, right? And so if you want to use lower embodied carbon materials, whatever they are, you got to watch durability. And that's where we've seen some challenges. And so we're going to see shift in the industry towards different materials or types of materials because of different reasons. And carbon's a driver, wildfire's another driver, we're seeing right now too. But when you look at carbon, just understanding how that material fails, is it water, is it whatever it is, and then designing for that. Now, the great thing about a rain screen is probably the safest environment to put these things in because you have drying in both directions, you have some redundancy, you can add other layers in there. And so if you are using more wood or bio-based materials, wood fiber insulation, hempcrete, hemp insulation, mushroom insulation, whatever it is, keep it dry. And a rain screen is going to be that safest, assembly to keep it dry. So a rain screen is a good, safe way to, use new things. There's sort of a joke, that a rain screen can have any cladding in the world can use on a rain screen. And it's almost somewhat true. Like you see all sorts of weird stuff sometimes put on this cladding because the backup wall is doing a lot of that work. That's just screening and essentially protecting everything else behind it. And so the control and a lot of everything's happening behind there, the heat, air, vapor control there, and whatever cladding you want to look on the outside. So if you take that design philosophy that A rain screen just allows you to do more, do whatever you want on the outside, make it look good, whatever material, some durability considerations, but the rest of the wall is doing your air, vapor, water, fire, and a lot of that are control, so you can have more design flexibility. So it opens up doors to architects and designers to do more rather than be constrained by direct fixing, systems that rely solely on that cladding.
It's certainly interesting times, as you say, with these changes and requirements around the carbon side of things. So, yeah, I look forward to seeing what's going to happen on that side. And Graham, thanks again for coming on board here. And, yeah, we'd love to have you back again sometime in the future if that's possible.
Oh, thanks. Of course, Simon. It's been fun.
Great. Bye then. Sharing knowledge is at the heart of our strategy to make buildings better for everyone. Sign up for our podcasts to learn more about creating healthy living conditions by protecting building structures from external and internal moisture damage. Thanks for listening. Looking forward to having you with us next time.